Hello everyone, I hope you are doing well. First of all, I would like to thank the organizers for giving me such a wonderful opportunity to present my work. My name is Saddam Hussain and I am a PhD scholar at Indian Institute of Technology, Kanpur. I will be discussing on non-minimal interaction of kessence field with dark matter fluid, and my collaborators are Anirban Chatterjee and Kaushik Bhattacharya. The outline of the talk is as follows. First, I'm going to talk about Hubble tension, and then I'm going to introduce interacting dark energy and then possible solutions associated with it. And then I'm going to talk about action of interacting dark energy and a little bit sheds light on dynamical system stability technique. And then we'll conclude this talk. We understand that lambda CDM model is one of the most successful model in the modern cosmology, and it fits excellently with several other data sets. However, when we are trying to measure a Hubble parameter or Hubble constant from indirectly or directly, there is discrepancy in the measurement, which is about 4.4 sigma level. So suppose that we are taking a CMB cosmic microwave background data and try to measure with the lambda CDM model Hubble parameter. It is coming out to be 66 to 68 kilometer per second per megaparsec. On the other hand, if you use Cepheid variables and supernova data, it found that H0 is between 73 to 74 kilometer per second per megaparsec. Thus, it shows that lambda CDM model is not working, and we have to look for some beyond lambda CDM model. So thus, people have already worked on various alternative theories, on which the most popular ones are early dark energy models, extra dark radiation, the period recombination, dynamical dark energy, in which the dark energy equation of a state becomes the function of redshift, interacting dark energy, in which dark matter and dark energy is interacting non-gravitationally, and some models depending on the modified gravity models like teleparallel gravity or FQ gravity. Now we are talking about mainly on interacting dark energy, in which the energy momentum tensor of dark matter and dark energy is no longer conserved, yet they are transferring the energy density. The exchange of energy density takes place via this Q term. So it says that these Q terms have been incorporated by hand in such a way that the total energy momentum tensor of the components has to be conserved. So if the Q is coming out to be positive, it says that the energy is transporting from dark energy to dark matter. On the other hand, for negative Q, dark matter releasing its energy to dark energy. Now, recently, Valentino and their collaboration have shown that if Q is depending on the dark energy density and the Hubble parameter, it is found that using the Planck 2018 data, Hubble constant is coming out to be 72.80 with Chi to be negative. So in Chi to be negative, it says that Q is negative, which implies that the dark matter is releasing its energy to dark energy, which actually manifesting that since dark energy is getting energy from dark matter, so it affects the Hubble rate, it affects the expansion rate in such a way that in the early universe, the Hubble, it increases the value of Hubble parameter, and thus we have H0 to be 72.8, which has elevated the tension at 1 sigma level. However, there is a problem with the interaction, because the interaction term has the less generalization, because in most of the literature, Q is proportional to the energy density or the product of energy density with the Hubble parameter. And thus it is associating with the lacking of physical motivation of Hubble parameter. The interaction depends on universal expansion rate H, which is introduced for the mathematical simplicity rather than physical motivation. One expects interaction to be played at each event rather than on global behavior of the universe. And by invoking the interaction term by hand, it introduced instability in the dark sector at the perturbation level. So what could be the possible solution for this interaction? What we understand is that this interaction at the covariant level can be achieved from the interacting Lagrangian. For an example, if you're writing the Lagrangian for the system for dark matter and dark energy, we have the Lagrangian for gravitational sector, Lagrangian for dark matter sector, which is let us say depending on psi, some dark energy for phi, and there is an interaction term, interaction Lagrangian, which is depending on both psi and phi. Now, if you take a variation with respect to metric, we have the field equation, the Friedmann equation, and the first Friedmann equation and the second Friedmann equation in the background of FLRW metric. What we are finding is that due to this interaction Lagrangian, there is associated extra term, that energy density of the interaction as well as the present interaction is coming. On the other hand, we have the continuity equation where Qm and Qde is coming from this interaction term, which is now again we are not saying that Qm is equal to basically minus of Qde. However, using the constraint coming from the interaction equation, it can be shown that this Qm will become minus of Qde it is giving the fact that the total energy momentum tensor has to be conserved. So this interaction can make this QM and QD to be negative of each other. Now, in order to understand the equivalence between the former interaction and the later one in the Lagrangian interaction, however, in the former interaction, there is no any interaction density and the pressure density. In both the situations, we have the total energy density which needs to be invariant. So if we use any linear transformation in such a way that between the bar term and the non-bar term, if any such transformation which does not change the total energy density or total pressure density, then we can say that these two pictures are basically basically denotes the same physics. However, if we are using the Lagrangian interaction formulation, then there is a various generalization that can be seen in terms of pressure and in terms of radiation density. Therefore, we are going to construct a action for interacting dark energy. So for that, we have taken a action in which the first term is showing the Einstein-Hilbert action, where R is the scalar, R is the Ricci scalar. And in the second term, we have the relativistic fluid action given by the Brown, where the rho is the energy density of the fluid, and depending on the number density and the entropy density, and J mu is the particle flux density, which is multiplying with phi, the Lagrange multipliers, comma theta. So phi, theta, beta, alpha are the Lagrange multipliers, and comma denotes the space-time derivative. So it is not a function of J mu. It is basically contracting with J mu. Now we have the action for the field, which is depending on the phi and the kinetic term x. And we have taken the two interactions. So one interaction is the kinetic interaction, where the kinetic term Fc is depending on number of fluid density, fluid parameters as well as field parameters. On the other hand, we have the derivative interaction, which has the additional contraction of particle flux density with the field velocity. Therefore, on the varying this action with respect to the metric, we have the Friedmann equation, and this Friedmann equation is equal to the energy density of the matter, the field, and in the interaction density. So we can easily identify these densities and the pressure by comparing with the stress tensor of the perfect fluid. So we can have the fluid density just like that, and we have the kinetic coupling density and derivative kinetic density just by comparing with the stress tensor of the perfect fluid. And over here we have the x is the derivative of the field phi, and it has to be always positive. Now we can easily find out the continuity equation for this coupling term, and from which we can extract the interaction term and the covariant derivative. And for the kinetic term, it is found that Q0 is just depending on the field derivative term. On the other hand, for the derivative coupling part, the interaction becomes the part of Hubble parameter. So if the particle flux density is contracting with the field velocity, then we can have the Hubble parameter in the interaction term. Now, similarly, if I am taking the variation with respect to phi for the action, we have the modified field equation for the kinetic coupling as well as derivative coupling. And similarly, we can realize the several thermodynamic quantities, just like variation of the action with respect to J mu, maybe entropy, as well as all these different Lagrange multipliers. We have the generalized thermodynamical variables in which d rho by ds is giving the temperature, and similarly temperature as well as the chemical potential also gets generalized. Now the system is becoming constrained using the variation of phi and theta. So in phi, we have the n dot plus 3 nh is equal to 0, which shows that the dark matter, because of the interaction, there is no any production of dark matter particle. So the dark matter particle is decaying as the universe is evolving and the system is evolving, and the dark matter fluid is remaining isentropic because there is no any production of entropy. The entropy is remain to be conserved. So now, because our model is so complex, so in order to understand the complexity of the model, we can use the dynamical stability technique, and we can achieve it by first defining the dimensionless variables. So first of all, there is a standard way to defining the dimensionless variable, like x is equal to phi dot. X and y is for the field parameter. Sigma is associated with the fluid density. Z is for the interaction density, and omega phi denotes the field fraction density. Now we are taking the kessence Lagrangian to be a product of potential and the kinetic term, and kinetic term is basically minus x plus x squared, which is derived from the string theory, and we are taking the potential of the kessence to be inverse type of law. So over here we have delta square over kappa square phi square. So over here delta is the free parameter which needs to be constrained from the dynamic system analysis. Now, first Friedman equation again gives us additional constraint on the fluid equation, fluid parameter, that sigma square is basically the basically fraction density of the fluid, and it has to be always positive between 0 to 1. It cannot be negative. On the other hand, we have several cosmological parameters, out of which we have omega total, which is effective equation of a state, defining as the ratio of pressure to the density. Now, in this case, it becomes generalized to P total over rho total. And similarly, for the kessence, we have the sound speed and in the rest frame, which again will get generalized because of the interaction term. Now, in order to have the model to be stable at the background level as well as at the perturbation level, it requires to between the CS square is required to between 0 to 1. If the model yields the CS square to be negative, it means that it introduces some instability at the perturbation level, and the model cannot be taken as the viable model, the physical viable model. Now, after that, we have first construct the autonomous equation by taking the derivative with respect to time, and then we have to find the critical points for this autonomous equation. And then corresponding to those critical points, we can construct the Jacobian matrix. Now, in order to understand the nature of these critical points, the Jacobian matrix will yield some eigenvalues, and based on the dimensionality of the autonomous system, in which we have the 3 cross 3 dimension or 3 dimension of autonomous equation. Therefore, we have the 3 eigenvalues, and based on the real part of these eigenvalues, we can infer the stability of the model. So suppose the real part is coming out to be positive, then the model is unstable. On the other hand, if we have the negative values, then the model can be taken as stable, and for the alternate sign, it is considered as a saddle solution. Now, for understanding the dynamics of this interaction, we are using the interacting model to be like most general possible and a exponential type. So we have m to be the dimension of the mass, and rho the fluid density, phi and x are the field parameters. So this interacting model yields several critical points, out of which we have chosen those critical points for which the interaction parameter z does not vanish. So for that point, we are estimating the omega effective, the total equation of the state in the two range. For example, in the green range, in the left, the green range shows the accelerating regime from -1 to -1/3. In the blue region shows the phantom region from -1.5 to -1. And based on the constraint on m and epsilon, we are plotting the corresponding eigenvalues, for which the eigenvalues has to be negative, so that the model is becoming stable. And we are understanding that if that critical point is showing us the late time cosmic acceleration or present time cosmic acceleration, then omega phi, the energy density of the field, has to be dominant, means that it requires to be from 0.65 to 1, and the sound speed has to be between 0 to 1. So in the blue region, we are plotting the eigenvalues, and in the yellow region, we are constraining the field density and the sound speed, and we are finding that if in the parametric space of beta and delta, using epsilon and m, which is coming from the effective equation of a state, we are finding the overlapping region. So the model, if we are choosing the model in such a way that the model is exhibiting accelerating solution, then we have an overlapping region. However, if we are using the epsilon m in such that it is pointing in the phantom region, then the model is yielding the stable solution. However, the sound speed becomes negative. So obviously, although it is it is presenting an accelerating solution in the background, however, it will give us instability at the perturbation level. So therefore, we are choosing the benchmark point in such a way that there is no any instability present at the background level as well as at the perturbation. Because of the interaction parameter, the phase space becomes non-compact, and therefore in order to compactify the phase space, we transform x, y, z in the capital X and Y, Z in such a way that it is tracking from -infinity to infinity. Now we are seeing that on evaluating the dynamics, the trajectory is originating from some part in the phase space, and then it is eventually going to A5. So A5 is the critical point, which is showing the stable critical point at which interaction is non-zero. On the other hand, we have several other critical points, A1, A2, A3, and 4, and showing the different regions of the system. In the right hand side, we have evaluating the cosmological parameters, just like in the blue we have cosmology, we have the field fraction density. In the red we have the fluid density. In green we have effective equation of a state, and the dotted orange line shows the evolution of sound speed. Now n is ranging from asymptotic past, which is representing as the negative values, and as we are going in the future, the positive values of n is showing the asymptotic future. So we see that at asymptotic past, the kessence field is acting like an radiation type of epoch, because omega total at this point is starting from 1/3, and as the systems evolves, the energy density of the fluid dominates over the field density, give us the matter type of signature, because at this point omega total becomes 0, and as we are entering at the present, then the fluid density becomes diminished, and the field density is about 0.70, and then in asymptotic future, the fluid density vanishes and the field density saturates towards 0.70 and near about. And at this point, the equation of state converges towards minus 0.99, and throughout the evolution, sound speed becomes from 1/3 to 0. So it shows that the model that is having the benchmark points epsilon 0.1 is consistent with is producing the stable accelerating solution in the background level, and it may also give the nice signature in the perturbation level. Therefore, to conclude it, the coupling introduced at the Lagrangian level generalized the interaction, making it easy to identify instabilities at the perturbation level. And we have constructed two types of coupling: one in which the interaction is function of both field and fluid parameter, and using dynamical analysis with an exponential interaction form, the model demonstrates stable accelerating solution during the late time phase. And in another, the field velocity couples with particle flux density J mu, resulting in Hubble parameter in the continuity equation. So we have added some references for the additional study of this field with the derivative coupling and the kinetic coupling we have explored in. So thank you very much.